program is running, but I haven't started streaming yet. There we go. And that was your question too? Thank you. Good job. All right. So we're going to be working on floating point 2 today in the lab. But for our discussion in class, we are going to we'll work on the logic of converting a value into the double representation. Because last time we talked about the double representation, so we know what it looks like, okay? We know what each bit within the 64-bit format is representing. So I'm assuming that you guys kept up with the notes in the lecture. So at the end of the previous lecture, I gave you an example, okay? I used GDB and input a whole bunch of hexadecimal digits into a 64-bit unsigned number, and then reinterpret those 64 bits as a double, and we got the value back. Okay, so if you don't remember that particular lecture, I strongly recommend that you watch the video from the last lecture. So what we'll do today is, okay, what about the conversion process? How do we convert a value into a double representation? Okay, so that's the focus of today's lecture. It will take more than one lecture to actually get through this stuff. So for the most part, we are just going to basically get it started, and then we'll see how far we can go. All right, so the conversion process is, okay, I'm going to assume that we are given a base 10 scientific notation, and we want to convert that into a double. Okay. And before we get here, I'm going to spend some time to talk about, okay, do I have it somewhere here? I apologize for all this scrolling, but let me see if I can find the syntax. There we go. Okay, so we'll start with this portion here, section 4, base 10 scientific notation. And we'll start with this description of a base 10 scientific notation that is normalized. Okay, you look at this bunch of characters and go like, what does that mean? Well, that's called regular expression. How many people have some exposure to regular expression prior to this class? Nobody. Good. Okay, some. Okay, one. Okay. That's good, because if everybody raised their hand and go like, oh man, I was just about to talk about regular expression because it's such a useful thing. So my note is not wasted in this case, because most people do not know what is regular expression. So regular expression is a way to in a very concise way describe what, in this case, what a base 10 scientific notation should look like. Okay, so we'll go through this thing step by step. The full explanation is actually in the notes itself as well. So, I suspect that you really don't need to write down anything much other than your own thoughts, okay? If you have a thought, your own understanding, that might be something that you want to write down. But everything on the projector, is already in the notes. So even if I forget to turn on the recorder, it's still there, okay? So I think we can just kind of focus on the idea. So the first part, which is the open square bracket plus minus close square bracket, is an optional thing. Anything that is enclosed in brackets is optional. What does that mean? It means you don't need that. Okay? It doesn't have to be there, but it can be there. But inside the square bracket would be the characters that are alternatives in that case. So in this case, if I specify open square bracket plus minus close square bracket, I take it back. Square bracket is just is a group. So we are looking at the plus and the minus character as a group in this case. So you can have one or the other, okay? So it is, in the sense, an alternative. It is plus or minus, okay? And the whole thing is grouped by the square bracket. They're alternatives. The part that specifies this is optional is backslash equal to. So backslash equal to is what we call an escape sequence, which means it is not literally the characters that you expect in a base 10 scientific notation. It is a it's kind of like a flag, okay? It's telling us whatever is immediately before can occur 0 or 1 time. That's all it says, okay? Backslash equal to is saying whatever thing that is immediately before the backslash equal to occurs 0 or 1 time, which basically means it's optional. Is that okay? So when you look at this entire thing, okay, let me highlight here what I mean by that. So when you look at this entire thing, it basically means a plus or a minus sign is optional at the very beginning of a base 10 scientific notation. That's all it says. Oh, but what if I don't want to be redundant and the value is non-negative? Can I just start with a digit? The answer is yeah. The sign is optional. Are we doing okay so far with the notation? Okay. So we move on to the next part, which is the backslash D. Okay, if you scroll down, if you're reading the notes on your own, or if you have a paper version of the note, you can actually read ahead of me a little bit. Backslash D is just saying this is a single digit. It specifies a single digit, which is from 0 to 9. There's an alternative way to specify a single digit, which is open square bracket, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, close square bracket. That takes up a lot of space. Okay, and that's why backslash D is typically what people use to specify a single digit. Okay, and single digit is now followed by a group of things, okay, a sequence of things. So we'll look at the open parenthesis that has a backslash in front of it, and the matching close parenthesis that also has a backslash in front of it. Now, the reason why there's a backslash is because regular expression can specify we really want parentheses to be a part of whatever I'm describing. But in this case, we are not saying that parentheses can be inside a only using the parentheses as a grouping mechanism to group, in this case, a sequence. So the backslash is an escape to let the either the compiler or the editor know that no, we are not literally talking about the parentheses that can appear as a part of the sequence. We parentheses to. Is that okay? So we have open and we have close parentheses that specifies a sequence. So the sequence is going to be whatever is specified between the parentheses, right? Between the open and the close. Yes? Yes. I'm pretty sure I can check. Yep, it is on. It's actually on the screen about here, so I can see it, but you guys cannot. For all we know, I can be watching a movie while teaching a class, and you guys cannot tell the difference. With closed captioning on, because otherwise I can't hear the conversations. Okay, so what about this part here? Backslash dot is specifying the actual decimal point. Okay, so I know this part is confusing because sometimes a backslash means, oh, the following symbol is not a part of the sequence. It is just a description. And in this case, it is actually part of what is in a sequence because a dot has a special meaning in regular expression. So if you don't want to use the special meaning of a dot, which basically means I can match any character, okay? That's what a dot means. But backslash dots basically just says, no, this is just the period, okay? Just that one single character. So we can have a single character, which is the period, followed by backslash D, and someone remind me what is backslash D again? A digit, right, from 0 to 9, but it specifies a digit, but it is followed by an asterisk. The asterisk is another, I would say, quantifier because it specifies what is immediately before that can occur any number of times. So in this case, let me just highlight the portion that I want to focus on right now. So in this case, backslash followed by an asterisk means any number of digits. Does that include 0? The answer is yes, it includes 0. So asterisk means 0 or more occurrences of the thing that is right before the asterisk. So what is right before the asterisk? Well, backslash D. So we can have any number of digits, including 0. Is that okay? All right, so now we can understand what the subsequence is specifying. Let me highlight the subsequence itself. So this is the entire subsequence, which basically starts with a mandatory period followed by any number of digits. Is that making any sense? Okay. But that subsequence is inside parentheses, right? So it is treated now as one thing. So when we move out to look at this entire thing, it is one group. And then we look at the symbol that is right after that, which is a backslash equal to. Remind me again, what is backslash equal to? It 0 or 1 time. Thank you. Very good. Okay, so backslash equal to is saying whatever is right before that can occur 0 or 1 time, or otherwise known as optional. It is optional. But that optional is now not only describing a digit, it is now describing the entire sequence of a period followed by any number of digits. Is that okay? So up to this point, okay, if I forget about the rest of the description, now we know that plus 0 meets this specification. We know that 0 point without anything after the decimal point also meets this requirement. We know that negative or minus 1.23 meets this requirement. Are we good so far? What about minus 0.5? Would that meet this requirement? Without the 0, right? Minus 0.5, which is what mathematicians and physicists usually would use, because they can save one character. But would it recognize that, or would it be meeting this requirement? It would not, because this digit here is mandatory. It is not optional. Okay? So this is a very concise way of describing what is syntactically correct and what is not syntactically correct. So up to this point, we have described this portion, which is what we know as the Mantissa in the scientific notation. Okay? Are we good so far? So the Mantissa is basically really just a number that has a single digit to the left-hand side of the decimal point, any number of digits to the right-hand side of a decimal point, if there's a decimal point, okay, with an optional sign that is at the very beginning of the entire number, and the sign can be positive. It's kind of redundant, but it will take it, or it is negative. Is that okay? So the rest specifies the exponent in a scientific notation. So when you look at the exponent component, this is the entire exponent sequence. Okay? What is right after the exponent sequence? Yep, go ahead.
So the plus or minus,
Uh-huh.
that part is optional because of the
Backslash equal to.
Okay.
Yep, because of the backslash equal to.
Just like the part after the decimal
Co-
point. The decimal point and the
Correct. The subsequence of the decimal point and any number of digits is also optional.
okay.
So, but focusing on what is highlighted right now, that subsequence is describing the exponent portion of a scientific notation. But what is the symbol right after that subsequence? Once again, we have a backslash equal to, and that means it is optional. So that means a scientific notation does not always need a exponent component. Okay, 3.14, okay, is already in scientific notation. It's good. Okay. But on the other hand, if you want to specify some really huge or really small numbers, then you can use the exponent, okay, to specify the magnitude of the number. The exponent is this part here, whatever is inside the parentheses is only this portion. Yep.
I was wondering, could you perhaps go over the slash parentheses again, the exact function of it?
It's just a group. It is the beginning, one marks the beginning, and the other one marks the end of a sequence. So there's a concept of a sequence as opposed to the concept of alternative characters. Square brackets specifies alternative characters. So if you say open square bracket A, B, C, D, E, F, G, close square bracket, what that means is one of the characters that you have listed. Okay? On the other hand, if you say backslash open paren, A, B, C, D, E, F, G, close, backslash close paren, that literally means A, B, C, D, E, F, G as a subsequence. But then you can use backslash equal to or some other quantifier to specify, okay, so is A, B, C, D, E, F, G as a sequence optional or not?
All right.
Okay? Okay, so now we are looking at a subsequence again. E has no special meaning in regular expression. So when you see lowercase e, it really just literally means lowercase e. Is that okay? So the lowercase e is followed by, in square bracket again, plus minus, which means, okay, choose. And then it specifies backslash equal to, which basically means or not. Okay? Choose one or the other of plus minus or not. And then followed by backslash d, which is a digit, right? This time we got something new, backslash plus. Backslash plus is the younger brother of asterisk, because asterisk says any occurrences, any number of occurrences, including 0. Backslash plus says one or more occurrences. So 0 is not an option. Okay? So what that boils down to is if you do have an E, then you have to have at least one digit after the E. Is that okay? Yep. That just specifies the period or the decimal point itself. Yeah, because a point by itself, a period by itself, specifies any character. So that's why we need a backslash to say that no, we are not meaning any character. We are meaning the exact decimal point character. Yep.
So how can we use a lowercase e? Is it representing the times 10 to a power, or is it representing like e as in a number? Because I've been kind of confused about that.
So the e is just a separator, so that we can separate the mantissa from the exponent. So that's the real function of e. And the reason why we choose the letter E is because it's exponent.
Okay. How come it's lowercase instead of like uppercase? That kind of.
I think it depends on the compiler. Some compilers will take uppercase E as well.
Depends on the notation.
Depends on the notation.
Tells you engineers for scientific notation.
Okay.
And we're in scientific notation. We're not in engineers notation because engineers notation has
Yeah.
a 3-digit.
Well, engineering notation has the exponent always as a multiple of 3. So you have kilo, mega, giga, tera, and so on. I think C and C++ will definitely, if a notation passes this test, it will definitely be accepted in C and C++. But I think C and C++ would also accept a wider range of notations. For instance, in C and C++, you have multiple digits before the decimal point. Okay? But in here, because I want to emphasize that we want to use a normalized representation, and that's why I only specify one digit here. And technically speaking, it should not be a 0. Okay? So technically speaking, if I want to be really restrictive, this backslash D at the first one really should be open square bracket 1 to 9 close square bracket, because I want to exclude 0 as the first digit or the digit before the decimal point. Okay, but I'm lazy. I'm just gonna this is easier. And if I want to change the syntax to accept both lowercase or uppercase e, to specify the exponent, then I would replace the lowercase e with a square bracket, lowercase e, uppercase e, close square bracket. Because then I have to choose one or the other, as long as it's not specified, as long as it's not followed by backslash equal to, it is not optional. You have to have one of those two. Yes?
What is the difference between the initial backslash D and the backslash D asterisk?
They are exactly the same thing. So every single backslash D specifies a digit in base 10. In other words, it's really the shorthand of open square bracket, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, close square bracket. So every single backslash D has that particular meaning. So are we good so far with this? Yes? Okay. Next question. Okay, next few questions. First one. Is this something that Tech invented just for this class to make his students go like, what are we talking about? Nope. This one, actually, as it turns out, is the syntax used by VI, the editor. So VI, or Visual, okay, that's the full name of VI, is an editor that can accept regular expression for searching. In other words, if you want to look for all the constants in scientific notation in a particular program, and you enter this mess here, it will find all of those occurrences. It can be handy, okay? I'm not gonna get too deep into what kind of tricks you can do with regular expression, especially in the case of an editor, but I'll just tell you it can be very, very useful. Because a lot of times, when you're programming, you're looking for something that is not an exact match, you're looking for a pattern. And regular expression is quite powerful when it comes to expressing a pattern. Okay, you can describe a pattern and go like, oh, okay, we can start with this. This is mandatory. You can have any number of this. Oh, by the way, this part is optional, and so on and so forth. Okay, it has its limits. Okay, there are limits as to what type of things can be specified using regular expression, but it is still quite useful, in normal, just text processing. Okay, and then some of you are thinking, but I don't use VI. I will never ever touch VI. Okay, then what is the purpose of doing this? Well, if you are going to go into any type of programming that involves validation of user input, okay, if you need to process any type of form, from the web as a form submission, on web application, you would probably benefit from understanding regular expression. That in a form there's a field for entering a zip code. Okay, well, how do you know a zip code is entered correctly? Well, they have to be all digits. Okay, fine. 1, 2, 3, 4, 5, 6. That's not a valid zip code. Okay, 5 digits then. 1, 2, 3, 4, 5. Okay, we're good. What about 1, 2, 3, 4, 5 with a period? Well, it is still a number, so if you check whether it's a number and it is less than or equal to 99,999, it will still pass that test. But it is not a valid zip code because you're not supposed to have that period after the last digit, and so on. What about the social security number? It's supposed to be 3 digits, a dash, 2 digits, a dash, and then 4 digits, right? And some of you are thinking, but I can just use string compare and or a loop to check all of this stuff. Yes, you can do that. But a lot of scripting languages like PHP, Python, JavaScript, Perl, just about any scripting language on the market right now, they have an engine to deal with regular expression, which means you don't need to write your own special subroutine to check that, oh, I just want 5 digits here, or I want 5-2-4 or whatever format. If you can specify regular expression, that's it. Okay, you don't need to write your own code for checking the syntax. You can just specify the pattern and have the regular expression engine in the scripting language to check it for you. Is that okay? So unless you think that I will never touch anything that has raw user input, regular expression can be useful in your future. Yes?
Can you show a small example of that?
Probably not during class time, because our focus is the real number in this case. But if you just look up regular expression, using Google search or YouTube, you will find plenty of tutorials and also explanation why it is useful in a lot of different scenarios. Okay, So this is regular expression. All we are now describing is what a base 10 scientific notation looks like. Okay, and I think we have a pretty good idea of what it looks like. I'll give you some examples, and then we'll move on to some other stuff, which is the actual conversion process. But before we move on, I just want to let you know what a number looks like based on this particular description. Okay, the simplest one you can specify is that. That is in scientific notation. Okay, that's in scientific notation. That is in scientific notation. That is in scientific notation. This is also in scientific notation. Yeah, some of these stuff is like, oh, what? But it's okay.
Third wouldn't pass
Huh?
the test, though, would it?
This one?
No, the third.
This one? It would.
Because of the
Because the backslash D is followed by an asterisk, which means any number of, including 0. Yeah. So it would pass the test. That would pass the test, right? That would pass the test. That would pass the test. That would not pass the test.
right.
Okay? So we get rid of the ones that do not pass the test. So are we getting a general idea of what we consider as scientific notation in base 10? Sort of? Okay. All right. So now the next question is, okay, fine, given a particular scientific notation, 1.23E45, which clearly meets all the rules, right? It's okay as a scientific notation. What do we do with it next? That's the next question. So I have to emphasize, the context of this discussion. We want to be able to parse a string. In other words, 1.23E45 will be given to you as a string, not as a numerical value. Okay? So just imagine you have double quote 1.23E45 and double quote in C or C++. It's really just an array of characters. Okay? ASCII code of 1, ASCII code of a period, ASCII code of 2, ASCII code of 3, and so on. Okay? The question is, given that string, how do you convert that string into the internal representation of a double that represents the actual value of 1.23 times 10 to the power of 45? That is the question. Is that okay? And some people know, about the function called ATOF, which stands for ASCII to float. Yes, that library function will do it, okay? But we want to make that library function. That's the whole purpose. We are reinventing the wheel, and in the process, we're trying to gain some understanding of what is a double and how does it relate to base 10 representation. Is that okay? All right? So the first thing we're going to do is to say, I don't want to use double to implement a parsing subroutine for double. In other words, all of the logic that I need to do this conversion, I want to do everything using only integer arithmetics. I don't want to use any double floating point number calculations. I don't want to use log. I don't want to use exponent. I don't want to use power. I just want to use integer arithmetic operations. Is that okay? Now, why? Because, hey, the Intel processor has got, several FPUs or floating point units. So, why waste resources on the processor? Well, the reason is, when you're doing something like this, you could be working with an Arduino, which is an 8-bit processor that has no floating point units whatsoever. So the moment you try to do any floating point calculations, it will get super duper slow. Okay, it's very inefficient. But if you want to do even 64-bit addition or subtraction, it's still relatively efficient with an 8-bit architecture like that. So we want to boil everything down to integer arithmetics. Okay, addition, subtraction, multiplication, and division. Is that okay? All right? Okay. So the first thing is, well, but how do we represent this using only integers? Because the Mantissa itself is already a non-integer. Okay? So what do we do? Well, let me ask you this question. Can I rewrite this? If I change the Mantissa to 123, which means I'm multiplying the Mantissa by 100, What do I need to do with the exponent in order to specify exactly the same value? Subtract 2. Okay, very good. So that means these two are the same, okay? But the right-hand side is not normalized anymore because the mantissa is now 123. It is not between 1 and almost 10. Is that okay? But this is what I need in order to boil everything down to integer arithmetics. Is that okay? So we look at this value, okay, we'll call this v. So let me just give it a name, okay? This is the value that we want to represent. Eventually, we want to boil this down to some base 2 mantissa m2 times 2 to the power of some e2, which is the exponent of 2. That is what we want to do. Without any base 10 components anymore, we want to boil this down to a mantissa that is specified in base 2 times 2 to the power of some number of e2. Because that will make it pretty easy to convert into a double at that point. Is that making any sense? Are we good?
Can you repeat that, please?
Okay. So M2 is a binary mantissa. Okay, let me just write here. M2 is a binary mantissa. It may be normalized because normalization is pretty easy to do. All we're doing is shifting things and changing the exponent. Okay, so whether it is normalized or not is not a big concern. The more bigger concern is E2 is an exponent of 2. That is the difficult part. We don't have an exponent of 10 anymore. See, there's no 10 to the power of something anymore. That is the difficult part. How do we get rid of 10 to the power of 43 in this case and somehow turn it into an exponent in base 2 and adjust the mantissa so that 123 times 10 to the power of 43 has exactly the same value or really close to some mantissa in base 2 times 2 to the power of some other power. That is the question. How do we do all this but not using math functions? Okay, when I say math functions, I'm referring to power, exponent, log, okay? But we can still use subtraction, multiplication, comparisons as long as they only involve integers. So that's the question. How do we do that? What do you think?
Find the difference of the largest base 2 exponent.
Okay.
The 10 to the power of 43 in this case.
Okay. So here's my recommendation. You read ahead of me in the notes. You guys knew this was coming, didn't you? Okay. So, but this really does, help. This is really the instruction, okay? It has all the instructions that we need to do all this conversion. But let's just focus on this one, okay? So we have 123 times 10 to the power of 43, okay? And we look at this and go like, oh, this is going to be problematic because, how do we convert this into everything in base 2? And someone may think, oh, we just have to figure out exactly what this value is, and then we just go through the normal process of base 2 conversion, and we're done, okay? Well, except, do you think this value will fit into a 64-bit integer? And how do we know that it does not? Well, because we know, even with a 64-bit unsigned integer, you can only have up to like 19 digits in base 10. Okay, I'm not exactly whether it's what the first digit is, but the point is there are only 19 digits. When you look at this particular value spelled out, how many digits do we have?
46.
46 digits. Does it even come close to 19? No. Okay, so that option is out. Okay, we cannot just multiply this whole thing out and say, okay, here's a 64-bit integer, and we just need to chop it off and do some bit shifting and get the binary representation. Nope, cannot do that. So then what do we do?
Convert the first part to base 2.
Convert the first part to base 2? Yeah, we can do that. Super duper easy, right? 123 convert it into base 2. That's easy. Okay. But the problem is the exponent of 10. That is the difficult part. Okay. The Mantissa is not too big of a deal. The problem is to the power of 10 to the power of something. Okay. So if I need to get rid of this, okay, if I need to make this smaller, okay, so that it becomes 42, what do I need to do? In other words, let me think about this. Okay, let me ask you this question. Can I do something like, okay, I will use just m here. Okay, I shouldn't use m because this Mantissa is not really in base 10 nor base 2. It is kind of like a just kind of mixed Mantissa. I'll call it mx. Okay, so we have an mx here times 10 to the power of 42, but I give you the option of saying, okay, we can also specify 2 to the power of something, and we can call this E2. Okay, so now the question is, what would that look like? And what do you think that is going to look like? In other words, we're trying to reduce the exponent of 10 just one at a time. But how can we do that? Okay, so we can think about this just purely from the arithmetic perspective, right? From the purely arithmetic perspective, what we are really trying to do is to say, oh, we have a let's see, we're reducing that by 1. Okay, so the first thing we can do, okay, so let me see if this is something that you guys can take here. Does that look okay to you? Okay, we're good here, right? Because all I'm doing is I'm reducing the exponent of 10 by 1, and then I multiply the Mantissa by 10, right? Okay. And let me move this up because I think people in the back may have a problem seeing this. There we go. And I can repeat this method, right? I can now say 100 times 123 times 10 to the power of 41, right? So I am reducing the power of 10, and up to now, hey, 123,000 is easily a number that I can represent using a 64-bit number. Is that right? Okay. So I can keep doing it like this up to a certain point, because we know that by the time this thing here has 16 digits, 1 followed by 16 zeros, then this amount can no longer be contained inside a 64-bit number. So we will run up to a certain limit at some point. Okay. So let's just say that this is where we run up to the limit. Okay. I know this is fictional, but we'll just kind of use that as an example. 1, 2, 3, 4, and times 10 to the power of 39. And let's just say that this is where we have to stop. Okay. The Mantissa can no longer, if I do this one more time, the Mantissa can no longer fit in a 64-bit number or whatever width integer that I'm dealing with. Okay, it's not quite there yet, but I don't feel like right. Okay, so then what do? We're kind of stuck now. Yep, go ahead.
We can reduce the exponent by making the base of the exponent 10 bigger.
Well, let me propose this, okay? Let me see, what am I going to say? Okay, so what about this, okay? I can, let's see. Okay, would that work for you? So when you look at 16 divided by 10 times 10 divided by 16, what happens? They just cancel out, right? Okay, that's fine. But what if I associate this multiplication by 10 here, and then we take care of this one by reducing it over here? Then we have 16 divided by 16, right? Okay. But it's still not really helping because we are still we're still changing the mantissa. So what do we need to do next? What if I introduce something like this? Okay. What if I now start to introduce 2 to the power of e2? So in this case, I'm not 100% sure about which one, but let's just say that we introduce this, okay? 2 to the power 4. But in order to maintain the same value, what do I need to do to the mantissa? Divided by 16. Very good. That is how we start to get rid of exponents of 10. We start to ramp up the power of 2, and then we start to divide the mantissa by the same power of 2. Is that okay? So by doing this repetitively, we can potentially shift, okay, quote unquote shift, all the powers of 10 to powers of 2. Is that okay? But in the process, we have division. Now, division is an interesting thing because in C and C++, integer division is always truncating. In other words, if you ask, okay, let me give you an example, okay? Keep this one here. But I'll give you an example of a little bit of an issue with division, okay? If you just look at integer division, what is 5/2 in C and C++? 2. It'll give you 2. Okay, very good. What about 50 divided by 3? It'll give you 16, okay? In other words, we're truncating the last portion. Everything that is to the right-hand side of the decimal point is truncated because it's integer division. It's automatically doing that. You don't have to do a single thing, okay? But that is potentially an issue because the result of the division is actually off from the actual answer a little bit. Is that making any sense? Okay. So if I look at 50 divided by 3, it is supposed to be 16.666666, right? So the error of the division is going to be 0.6666 divided by 16.666666, right? Am I making any sense? Okay. So if you look at the error, okay, and we'll look at some extreme case here. 3 divided by 2 is 1 in using integer math, right? But how does it compare to the actual answer? What is the actual value of 3 divided by 2? 1.5, right? So what is the error? The error is how much off it is from the actual value. So in this case, the error is 33.33333%. Is that okay? Not really that good. So now we look into a larger version of this. Okay, let's say we're looking at 33 divided by 2. 33 divided by 2 integer math is going to give you 16, right? But what is the error? The error in this case is 1 divided by the actual answer, which is 16.5. And that is going to be a smaller number. I think it's in 6 point something percent, 6 point something percent. Is that okay? But can you see, how even though the divisor is the same, but if the dividend is larger, then the error goes down. Okay? Just to give you an even more extreme example, let's say we have 1001 divided by 2. Okay? So the integer math is going to tell you it's 500. But what is the error? The error is 1 over 500.5, okay? And that's, okay, I'm going to use this to say approximately equal to. So it is approximately what? It's 1/5 of a percent, which is about 0.2%. Okay? Not exactly, but it's pretty close to 0.2%. So do you see how if I increase the dividend, I can lower the error? Okay? So that means if I want to do some trick like this, okay, to divide the mantissa by some power of 2, I want to crank up the mantissa as much as I can before the division by some power of 2. Does it make sense to you? So how do I crank up the mantissa? Well, in this case, we got a lot of ways to crank up the mantissa, don't we? Because we still have a 10 to the power of 39, right? So we can keep decreasing the exponent of 10 and multiplying the mantissa by 10, make it as big as possible. And then when it is like the last number or the last value that can be represented using a 64-bit number, then we go like divided by 16. That's much smaller compared to this. Does that make sense? Okay, so that is how we get rid of powers of 10. Okay, we're out of time today, but for the notes, so what I want you guys to do, besides working on the lab, which I will release, soon, is to read section 5.1 as well as section 5.2. Okay, those two sections will help you understand, how to write a program to do this conversion, which is basically what we'll eventually end up doing, is to write a very small program to do the conversion. It sounds more difficult than it really is. Okay, so I'm gonna stop the recorder.